Himalayas' height had helped by elevated tectonic plates. A new study challenges conventional mountain building understanding, sending the field in some interesting new directions. Stanford geoscientists have upended conventional thinking about the formation of mountain ranges, shedding new light on the creation of one of the world's most iconic peaks, the Himalayas. The findings published in Nature Geoscience on August 10 introduce a fresh perspective on the role of tectonic collisions in shaping these majestic formations. The Himalayas. Traditionally, the prevailing theory held that the Himalayas resulted from the collision of tectonic plates. However, the study challenges this notion by revealing that the edges of these plates were significantly elevated even before the collision occurred. The team, led by Paige Chamberlain, a Dorr School of Sustainability professor, found evidence suggesting that these plate edges were about 3.5 kilometers high on average, accounting for more than 60% of their present height. That's a lot higher than many thought, and this new understanding could reshape theories about past climate and biodiversity, emphasized first author Daniel Ibarra, an assistant professor at Brown University, in a press release. The study's significance lies in its innovative approach to paleoaltimetry, which involves assessing past altitudes. By analyzing the isotopic composition of rocks, scientists can infer the height at which those rocks were formed. The technique relies on oxygen isotopes, mainly oxygen-17, showcasing unique precipitation patterns at varying altitudes. Oxygen-17 is exceptionally scarce, constituting only 0.04% of Earth's oxygen. Just think, a sample of 1 million oxygen atoms will contain a mere 4 oxygen-17 isotopes. There are maybe 8 labs in the world that can do this triple analysis, noted Chamberlain, who aided in sample processing at Stanford's Terrestrial Paleoclimate Lab. Still, it took us 3 years to get numbers that made some sense and that were working every day. A rare oxygen isotope. The press release highlighted that this explains why triple oxygen analysis had been neglected, or maybe too readily disregarded, as an indicator of past altitude. Hence, this recent study seizes an opportunity. Collaborating with researchers from China University of Geosciences, Beijing, the Stanford team initially tested their technique in the Sun Valley, Idaho mountains, before applying it to the Himalayas. Moreover, by extracting quartz veins from lower altitudes in southern Tibet and applying triple oxygen analysis, the researchers demonstrated that the origins of the Ganges Arc had considerably greater elevation than expected well before any tectonic collision transpired. Experts have long thought that it takes a massive tectonic collision, on the order of continent-to-continent scale, to produce the sort of uplift required to produce Himalaya-scale elevations, Ibarra added. This study disproves that and sends the field in some interesting new directions. The study's implications extend to broader theories about climate and topography, potentially influencing our understanding of other mountain ranges like the Andes and the Sierra Nevada. Thanks for watching.